Good morning, everyone. I want to talk today about motion planning for mobile robots. So how should mobile robots move through the environment in order to go from a location A where they are right now, for example, towards a target location where they want to end up with. And can do this using planning algorithms or graph search algorithms. And a very popular informed search algorithm is the A-star algorithm, and that's the approach that we will be using today in order to solve the path planning problem or motion planning problem for mobile robots. Motion planning is a very traditional, very common problem in robotics, and there's a huge body of literature describing how we can plan trajectories for mobile robots, for manipulators, for complex systems in static environments, in dynamic environments, in high-dimensional spaces, in low-dimensional spaces. So there's a large zoo of different approaches that have been used in order to decide how a system should navigate through the environment. But motion planning itself, as Tom pointed out in 1991 in his motion planning book, is one of the essential capabilities of those robots because they need to achieve something useful, typically by moving through the real world. And by deciding to decide how to move through the real world is something that is strongly related to the motion planning problem. So if you want to have a robot that navigates through the environment, what are kind of key requirements that we typically want to achieve? The first thing is our path should be collision-free. So the robot should not collide with, for example, an obstacle in the world. It should not bump into walls. That's something that we don't want to have. This may also be seen as dynamic obstacles that the robot needs to avoid. So if you have people walking through the environment, the robot, of course, should also not collide with people, even if they are not stored in the internal map representation of the robot, for example. And the second thing we want to achieve, besides having collision-free trajectories, is that we typically want to achieve the target location as fast as possible. So we want to minimize the time that it takes the system to reach the target location. Again, there may be reasons to deviate from this approach by saying we want to optimize something else, like in as smooth as possible movement, or that if you have a vehicle that has passengers on board, so that it's as comfortable as possible for our passengers under the constraint of being collision-free. So there are variations of those two goals which are listed here, but these are, let's say, the most common goals that we will find in the robotics literature when we talk about path planning for mobile robots. And at the same point in time, the system should be able to deal with dynamic environments. That means environments in which things changed. That can be people moving through the environment. This can be static objects which have been placed at locations where the robot is not aware of that fact. And this makes the planning problem more complex. It needs then to be tightly coupled with our observation systems, so with our sensors such as a laser rangefinder, in order to estimate where there are obstacles and how to plan or replan a trajectory in order to reach the target location in a collision-free manner, still as efficient as possible. So the main question is, how do we react to those unforeseen static or moving obstacles? How do we do that efficiently, and how do we do that reliably? And there's a large number of different techniques that have been proposed. For example, dynamic window approaches are reactive techniques that try to drive around obstacles, approaches that use grid maps for planning. We have other local techniques like the nearness diagram, which basically takes your local sensor information into account and makes all the decision based on those local information, and a large number of techniques that rely on path planning. And this is the set of approaches down here. So A-star is probably the most commonly known ones, also an algorithm that you know already from your algorithm theory or your geoinformation lectures that you have attended. There are variants of this like D-star or D-star Lite, which are approaches towards replanning. So whenever you need to replan because the environment is changing, how can we avoid to plan everything from scratch again? How can we reuse things we already know to optimize the processes? Something that the D-star family of algorithms originally developed by Dave Ferguson is doing, or ARA-star, which is anytime real-time A-star, where we try to reduce the computational load of the algorithm by accepting that our trajectory may be suboptimal. So we don't find the optimal solution, but are able to find a solution very quickly. These are approaches which typically plan the trajectories, assuming that there's no uncertainty involved, no uncertainty in the observations, no uncertainty in the map, no uncertainty in the motion execution. If you want to relax this assumption, such as the uncertainty in the motion execution, then you typically end up having a Markov decision process that you need to solve, or an MDP that makes the planning more complex. So for this lecture today, we will stay in the world of A star, but we are going to extend this in the upcoming lectures, looking into navigation when we have uncertainty involved, especially uncertainty in the motion estimate. Okay, so to wrap that up, we are looking into planning, assuming we can trust our sensor observation, so we know in which state we are in, and we want to generate fast and collision-free trajectories. So what are our key challenges in here? Key challenges are, first we want to compute the optimal path. That means there should be no better path than the path that we select. We in some applications can relax this assumption. That is not necessarily the optimal path, but we at least want to stay close to the optimal path. Also, taking into account uncertainties, as I mentioned before, for example, in the actions, can be a challenge. Most of the time, the planning algorithms that we are using don't do that, but we can do some tricks in order to kind of avoid the most common mistakes or suboptimal decisions that planning algorithms do if they ignore uncertainty, and through a small trick integrate at least some awareness of uncertainty into the planning process. It's also something we'll look into, and which basically most planning systems do today. We also want to be able to quickly react to unforeseen obstacles. That means if the system is driving through the environment and a person steps out of a blind spot and stands in front of the robot should be able to react very quickly and either brake or make a detour and drive around that unforeseen obstacles. And even as a next challenge, we can even say we have moving obstacles, so objects that move through the environment, so that the robot cannot assume the world to be static at every point in time when planning a detour, for example, but must take into account that the object is actually moving through the world. So these are different challenges, and we will start basically by looking into how to plan the optimal path, then maybe take into account how can we deal with some levels of uncertainty and how can we quickly react to unforeseen objects. In most robotic systems, we will have a layered architecture, so to say, that different parts of the motion generation problem happen at different layers which run at different frequencies. So on the top layer, we typically have what we call the general planning approach, or planning system. That typically takes into account a map of the environment, here shown as a 2D occupancy grid map. It also takes the sensor data into account, or the sensor data is already integrated into the map and then it just uses the map. That's another alternative how you can do this. And typically provides the obstacle information. This happens at a low frequency. Let's say every second or every 5 seconds you replan a path on a global scale. Sometimes you have systems which are fast enough that you can execute this more frequently, maybe going down to 1/10 of a second, but this basically depends on how fast your system is moving. It's obviously different if you have a robot navigating an indoor environment with, let's say, 50 centimeters per second, or if you're an autonomous car driving with 100 kilometers per hour over on the highway, then of course you will need to have different reaction times, but I think that should be pretty clear. For typical robotics architectures, we then have a collision avoidance layer, and this collision avoidance layer typically performs some very local navigation. So it gets a local goal or a sub-goal from the planning system, let's say the position 5 meters ahead on the trajectory that the planning system has actually generated. And then the collision avoidance system tries to reach this location, but making sure that the movements are collision-free. So it takes into account the sensor data and also often uses the map or at least some local representation, if there's an obstacle, yes or no, like blocked out regions, but not the whole map, and then tries to react very quickly at the sensor frame rate, let's say 10 times per second, 20 times per second, 40 times per second, depending on the application, in order to generate trajectories which are collision-free or execute an emergency braking behavior. And this simply runs on a much higher frequency than this low-level planning system. And so this needs to be done in order to be able to react to obstacles very quickly. And then these local collision avoidance systems typically generate a motion command. Often this is, let's say, a translation velocity and a rotational velocity, or a steering angle and a translation velocity, that then the system maps into the actual speed of the wheels. So the controller, which sits here at the bottom, sometimes this is still integrated into the software system. Sometimes this happens inside the robot. That depends a bit on the hardware configuration that you have. And we are talking today here about the planning layer. So we're sitting here most of the time. That's where the A-star algorithm is used, at least in most cases. But we can also actually move that a little bit down and integrate this also in the collision avoidance layer, at least if we can execute our planning system fast enough. If this is not the case, that it is fast enough, then this can be replaced by a different model, such as dynamic window approach techniques, for example. But for now, we'll start here with that planning level. So what is the motion planning problem? In the motion planning problem, what we have typically given, we have a starting pose, or often that's the current position of the robot, and that's the point from which we start. So here we start, and in the end, the robot should reach a goal location, which is the second input. So where should the system be? This can be an XY location in the environment. This can also be an XY location in an orientation. This could be a 3D location with an orientation. That may be even a location and orientation and a speed that the system should have at that point in time. So there are different variants and different spaces that you're actually planning in, depending on how you specify your target location and your goal location. What we typically also have is a geometric description of the environment, or not only the environment, but the robot as well as the environment. So we need to know what does the world look like around us. And this is typically done with the geometric description, such as an occupancy grid map, but this can also be a topological representation of the environment. And we need to know something about the robot itself, for example, its geometry, what are its extents, because we need to make the decision, for example, if the robot fits through a narrow passage, does it fit through a doorway? That's information that we need to have available in order to perform the planning system in an appropriate way. And given this input, what we want is the shortest pass, or the optimal pass under some other cost function that gradually moves the robot from the start location to the goal location, never colliding with an obstacle. And that's basically what we refer to most of the time as a planning problem. And again, we said a short path, or the optimal path, or the shortest path, or the path that minimizes certain accelerations, for example, or jerks. These are different things that, depending on your planning problem, you want to take into account. But in the end, it's a cost optimal path, and the costs are quite often related to how fast, how much time does it take the system to actually reach that configuration. So the configuration space is also some important concept to talk about. Although the robot typically moves through our real world, our Cartesian world, the planning problem typically lives in a different space, in the so-called configuration space, also called C space. And it can be seen as the positions of all robot points relative to a given coordinate system. And so this can be different from our X, Y, Z space as we know it. For example, if we have a manipulator arm and we have joints describing or angles describing in which configuration joints are in, then the configuration space is kind of the whole geometry of the arm of the robot, but we can internally represent it, for example, with just using the angular components of our joints. So the space in which we perform the planning may be different from our real world. And quite often this configuration space is discretized, and we're using a discretized version of that space in order to perform that planning. So what does it mean? This is a short example of kind of the 2D world and breaking down the 2D world into kind of something very similar to a grid map. So we have spaces in the environment which are occupied by an obstacle, are these green regions, and then we have these white cells, which is free space. And you can see actually a node in all of those white cells. And these are positions where the robot can be in. And here, again, this is an abstraction, assuming the robot can just be in the middle of one of those free cells. And then this discretization of the state space shows me all possible states the system can be in, which are all those dots here. And those dots are actually connected with each other depending on the connectivity in that map. And by finding a path through that graph, for example, from a start location to a goal location in this example, we are able to describe how the system should move through the environment, and often again this happens in this discretized space. It doesn't have to be discretized, but quite often we are working in discretized spaces because the continuous space is very tricky to represent, may not be a uniform discretization as it's done here. Also sampling-based techniques are other alternative to subsample the possible states the system can be in. So we can describe this also a bit more formally, looking into the free space and the obstacle regions. So we can say we have certain regions which are here represented by obstacles, and we have certain regions that are here free space, now here illustrated in a continuous space. And then we can say what is the free space, what is the occupied space. The free space is basically the space in configuration space, so all possible configurations. The intersection between all the positions of the robot given a certain configuration, this is A of Q, so given a configuration of a configuration in this configuration space, these are all possible positions that the robot takes, so because the robot has a certain extent. If I'm intersecting this with all the obstacles that I have, and this is the empty set, then the configuration Q lives in the free space. And then the obstacle space is basically the complete configuration space except of the free space. And we are interested in planning only in this free space. So we want to have a start configuration and a goal configuration in this free space, and then want to find a trajectory or a path that guides me within this free space from my start location to my goal location. So the system starts here, and I want to define a path so that the path parameterized with an input of 0 is the initial configuration, and for example with an input of 1 gives me the goal configuration, and the path that completely passes through the free space. So that means that the goal location and the initial location are connected in the same free space, and that I can define a path which guides me from the configuration, the initial configuration to the target configuration throughout this connected free space. And this is then the solution to my planning problem. Again, as I said, the state space or the configuration space, sorry, is typically discretized for the planning problem, and there are in general two different approaches how we can do this. The one thing is so-called combinatorial planning approaches, where we are basically using like the uniform grid that I've shown before, and basically generate nodes for every possible location the system can be in, and then connect those neighboring nodes and then try to find a path through that graph or perform a search in this graph. The problem is with this, the complexity grows exponentially with the number of dimensions that need to be involved. So that is something that may work for low dimensional spaces, but is much harder for higher dimensional spaces. An alternative approach is the sampling-based planning systems, which basically sample possible configuration often in a randomized fashion, and then have a local collision detection system that says, is this configuration in the free space or in the occluded space? And then with a kind of the configuration the system samples is typically close to an existing configuration in the free space, and we have some way for connecting those nodes, for example, with the local planner, or with the collision avoidance check at least can verify that there's a connection between those sampled nodes. And then I can actually sample nodes and in this way explore my free space until I reach my goal location. Of course, I can use things like heuristics or techniques which guide me or pull the sampling towards the goal location, because otherwise it can be also computationally very expensive. But these are basically the two ways how we typically discretize our C space. So either discretizing it based uniformly through all dimensions, or with a sampling-based approach. And what we then do once we have such a discretization of the space, we performing a search and finding a sequence of states that guide me from the current location to the target location. And typically these states are, or the transition from one state to another state are attached to actions. This can be a steering command such as a translation velocity and a rotation velocity that guides the system from one state to the next state. And basically following this path from the current configuration into the goal configuration. And this search can happen in different ways. The standard approach is the so-called uninformed search. Here, the system doesn't have any further information about where the goal is. It's also called blind search for this purpose. And we're basically extending states until we find the goal state. And it's basically only the question in which order do we define neighboring states. And there are different ways how that can be done. And this is the so-called uninformed search. Common representatives are breadth-first search or depth-first search as probably the most prominent examples that you all have seen when you're looking into search algorithms. But often we have some information about our space. And so in robotics, we can often do a better job by exploiting some information that we have. For example, the fact that we know the robot often lives in a Euclidean world. And already the fact that it's a Euclidean world and that these are X, Y locations, for example, allows us to do better than uninformed search, because the coordinates where we are right now and where the goal location is may tell us something already about the direction in which we should move in order to come closer to our goal location. And this is something that we exploit in the context of informed search. So informed search uses further information about the space the system is in or the robot is in order to guide the search, in order to push the search into potentially the right direction. And that is something that we often call a heuristic. So we'll use a heuristic function that will tell us something about how likely it is that I'm actually coming closer to my goal, at least an estimate. There doesn't need to be the correct information. It can be just a guess. The system is tailored to move towards this guess. And we can say, what are the most promising locations to expand? And the system will simply prefer to expand more promising locations first in order to come closer or more quickly to the goal. And if those potentially more promising locations are not the right way to go, the system will expand the others one, but will do it later in time. And so the planning system therefore is typically faster if you have an informed search at hand. And the prominent examples for this informed search is actually the A-star algorithm. And so there's a large number of different search algorithms that are out there, and they are evaluated under different properties. So different things may be important to us if we need to select the search algorithm that we want to use for our robotic problem. So for example, completeness is one of those things. And completeness basically means if there exists a path from my initial configuration to my goal location, will the system actually find it? It may be the case that it is an algorithm that even though there exists a path, it's unlikely or it cannot be guaranteed that the system actually finds this path. This is something which can happen for sample-based planning algorithms, especially if you don't have an infinite amount of time, only a finite time horizon. Optimality is a second very important criterion. So is the path that the system actually generates the optimal path or not? Optimal means here optimal under the chosen cost function. If your cost function that you want to minimize the time, that means there should be no path on which you can go faster to the goal than the one the system has reported. There may be multiple paths which let you reach the target location in the same amount of time, but you want to make sure you find a path that has this minimum requirement. Also, for shortest path, it's the same if you're not minimizing travel time, but distance, which is often related, but often also not the same. Then you want to find the shortest path. That means there should be no other trajectory which is shorter than the one that your system has found. And these are two very important properties that we need to look into. The other thing which is important for us is the time complexity and the space complexity. So the question is, how long does it actually take to find a solution, and how long is typically not measured here in terms of whatever seconds, minutes, hours, but also with respect to how many nodes need to be expended with respect to the complexity analysis, for example, using the O notation. So you're basically interested on how many expansions of states are needed given a certain number of states and an average neighborhood relationship, for example. The other question is space complexity. So how much memory does your system need to have with respect to the number of states that we find in order to compute your solution? These two things are also important properties. So basically, how fast or how efficient can you actually compute your search? And those two things tell you something about the result that you get. So do I find a result, a solution in case it exists, and is it actually the best one which is out there, given the cost function that we have been using? Okay, so how could we do that? Let's start very briefly with uninformed search. We have breadth first search and depth first search, which are the two very common search techniques that you know. And if you have your search tree, so you start from this location 1 and you continuously expand those neighbors. So the neighbors of 1 would be 2, 3, and 4, and the neighbors of 2 would be 5 and 6, and so on and so forth. So in which order do you actually search through those states? And you basically go here level by level. So you will start at 1, you expand 2, then 3, then 4, and then you look to the neighbors of 2, which is 5 and 6, then to 3, the neighbors has no neighbors of 4, 7 and 8, and then 9, 10, 11, 12. So level by level, you are expanding that tree. And this you basically uniformly extend your radius, kind of. If this is your start location, you're basically building, at least in the 2D world, concentric circles around the current configuration until you reach your start location. It's a complete algorithm. It's optimal if the action costs are equal. So if all those costs have equal cost, otherwise you may have paths which are very cheap and paths which are very expensive, and those expensive ones may be found before the cheap ones because you're going at level by level and not based on the cost that you have found so far. In depth first search, you would start here with this node 1, so you go to the node 2, its first neighbor, and then you don't look to the other neighbors. You're basically going down in that tree by first always expanding the neighbor. So you don't go level by level, you're basically going deep first. And so this would be the order we would expand the tree: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So because you first expand the neighbor, the next neighbors, and not the one on the level first. Also some properties, it's not complete at least in infinite spaces. So if this tree can be arbitrarily long, and this would be the optimal path. If you just search in this direction, you will never find the optimal path. Also not necessarily find a path at all. It's also not necessarily the optimal solution, and has certain properties with respect to space and time, which depends on the branching factor, how far the goal is away, and the maximum depth of that tree. These are standard algorithms which are out there, but these are algorithms which are often not used in robotics. A star is different in here because what A star does, it uses some additional knowledge about the environment. So far, we haven't used any additional knowledge that was known beforehand, and A star does it by using a so-called heuristic. And the heuristic is an estimate how expensive is it from a node to reach the target, the goal location. Of course, that is something that is not known exactly, but maybe we are able to estimate that cost. So for example, in the Euclidean space, the straight line distance between two coordinates is an approximation of the actual cost or the actual distance between those two nodes. So again, if I'm planning in the space of distances and I want to estimate how far is it from a location, let's say 1, 1 to location 2, 2, and by not knowing how the environment looks like, a good estimate could be square root of 2, because this would be the straight line distance between those 2 points. Maybe the distance is longer if there's an obstacle in between and the system needs to make a detour, but at least I have an estimate on how far those 2 points are away. And exploiting these estimates, these heuristics in the search, is something that the A-star algorithm does, and which makes the A-star algorithm so efficient. So we use the A-star algorithm typically in robotics to plan a path from a start location to a goal location. we assume to have a map of the environment, something like an occupancy grid map, so where we know which parts of the space are occupied, so which we are not allowed to enter, and which parts of the environment is free space, which we are allowed to enter. And then we are actually providing a sequence of neighboring states, so states in the grid map which are connected through the 8 neighborhood or 4 neighborhood, for example, and then return this as a path. And what we are using here is the additional information, such as information about straight line distance. And also I have a small example over here. So we have an informed search. We are here in the start location. We want to reach that goal location. And by starting the video, you will actually see how the different nodes will be expanded, trying to find a path from the start location to the goal location. So you can see here the system expanding the states. We have those dark states, which are those states which have been fully expanded. And then we have the boundaries, which are here shown in these light states with gray. And the system started over here extending those states, the states until it reaches the goal location. And then once it reaches the goal location, it knows that it was the shortest path from the start to the goal by just following the sequence of expansions, of cheapest expansions that it has done. Other parts of the state space, like these rooms over here, have not been explored, so the search algorithm has never visited those states. And what the heuristic basically does, the heuristic drags the expansion of those nodes towards the goal location. So I'm expanding nodes here starting from the start location. I'm evaluating all of those nodes not only based on the cost, how far was it to reach this node given the start location, but we also perform an estimate how expensive is it most likely to be from this location to my goal location. And this is the information that the heuristic provides us. And we are exploiting this heuristic in order to focus the search among the remaining nodes to expand to say which one is probably the best one to expand based on this heuristic, based on this guess about the cost. Again, the heuristic is not the exact cost, it's just a guess about those costs. But it has to have certain properties in order to allow us to come up with the correct solution. So what A star does, it basically performs the estimated cost, which consists of costs and a heuristic. So the cost that it actually takes plus estimated heuristic. And so what we have in here is we have the cost G, which is the actual cost from my initial state to a current state n. So G of n is a cost function of a node. How expensive is it from the initial state to reach this node n? And then we have the heuristic, which is the estimated cost. But again, now not from the start location, but from the location n to the goal location. Okay, so G is basically the computed cost expansion from initial state to n, and the heuristic tells me how expensive is it got from this node n towards my goal location. And then the cost function that A star uses, often referred to as f of n, is the sum of those two costs. So the cost to go from the start to a node n plus the estimated cost from n to the goal. And this is kind of the best estimate that the algorithm has how valuable this state is for finding a shortest path or cost optimal path to that goal. So what A star does, it basically always expands the node which has the minimum f cost. So where we have the minimum of in the sum between the actual cost so far and the estimated cost which are to come. And it will always expand the node with the smallest f cost until it reached the goal location. We however have to say a few words about this h of n, about this heuristic. What are properties that this heuristic need to satisfy? The first thing we want to have is that the cost of the target location is 0. So if we are at the goal location, we should get a cost of 0. And the second thing is that this heuristic should always underestimate the real cost, or underestimate or be identical to the real cost. So, and this is when we call a heuristic admissible. That means assuming we would know the perfect cost, so that would be basically the result of our planning algorithm already. We wouldn't need to plan, we would just need to follow a gradient. But this is what is called H star, the perfect heuristic. These are the actual cost from the current state n towards the goal location. And if I would know that, then of course I should use the optimal heuristic, because then there's no estimate involved anymore. But I don't have that. What I however need to guarantee is that the heuristic that I'm actually using is smaller or equal to this optimal heuristic. So you may ask yourself, how can I actually specify this, given that I don't know what the actual costs are? But often you can do that. Consider again my example with the straight line distance between 2 points. You know that if you have 2 points in a Euclidean space, the straight line distance is the shortest connection between those 2 points. So if everything is free space, this connection between those 2 points is actually the shortest path from one to the other. If there's an obstacle in between this trajectory, then this is not the case. Then the system needs to make a detour and go somewhere else. And so we know that the straight line distance is an admissible heuristic for the Euclidean space, because it either estimates perfectly or underestimates the actual cost. And if the nodes are the same, the Euclidean distance is 0, so we also end up providing the actual cost. So this is something which we need to take into account, that the heuristic is admissible, because if the heuristic is not admissible, then we will still find a solution, but we are not going to find the optimal solution. You can actually show if the actual heuristic would, let's say, overestimate the optimal heuristic up to a factor of 2, so it's larger than it's allowed to be by up to a factor of 2, then the solution that I can get out can be twice as bad as the actual optimal solution. So the factor which sits in front of the heuristic is also the factor that you get in your bounds on finding the optimal path. In practice, however, it's not that bad. So even if you overestimate your heuristic, so assign higher costs than there actually are, your searchability is faster, you find a suboptimal solution, but in most real-world situations, at least in this Euclidean space where we are working with robots, the path is not, for example, twice as bad as the actual path. And this effect of expanding the heuristic, increasing heuristic with a factor larger than 1, is something that some of the speed-up techniques like anytime real-time A star is using in order to more quickly find an initial path to the goal, and then if more computational time is available, optimize this path and reduce it or reduce the cost of this potentially suboptimal path, but having a path at all point in time. So to sum up, what A star does, it uses the actual cost plus the estimated cost as a sum, so F is G plus H, and we have some constraints on H that H must be admissible if we want to find the optimal solution. And then the A star algorithm can be easily formulated as a search by saying we have our A star, and just see the block diagram here taken from Harry Choset's book. So we start at the start location, and then we have 2 lists or queues, O and C. So O is the open list and C is the closed or covered list. So O is the nodes that we still need to take into account, C are those which we don't need to touch anymore. So we start if this open list is empty, and initially I put my initial configuration in there. If it is empty, then we are done. If it's not empty, which is the case initially, we pick the best or the best node, so the node with the smallest cost from that queue, so the one which has the smallest value, and therefore we're typically using a priority queue because it automatically sorts them for us and take out the smallest cost. Then we take it out of the open list and add it to the closed list because nothing needs to be done anymore. I check, is this the best node? If it is the best, if this the best one, so the one that I popped from my open list is actually the goal location, then I'm done. But most of the time it will not be the goal location. So what I then do, I'm expanding all the neighbors of that node that I taken out of this open list, and all of those which are not in the closed list, so which are not already completed, have been treated, then I need to do the following thing. So if it is already in the open list, then I need to update the cost by checking if the new cost that I have of reaching this goal is cheaper than the cost that the node already had. That means I found a detour for taking a node that is still in my open list, so a node that I need to consider that I didn't know beforehand. Or if this is not the case, so if it is not in the open list, then I simply add it to. Then it's a node which I haven't looked at yet and still need to look at. And then I'm kind of going back to this to my open list, check if the open list is empty. If this is the case, no solution is found. If it is not empty, then I continue taking out the cheapest element, the one with the minimum cost, and checking is it the goal, then checking all its neighbors. Are the neighbors already in my open list? If this is the case, I need to check if I need to update the cost. Otherwise, I add them to the open list and continue this process until I have found the goal, then I have a solution, or my open list is empty, then I don't have a solution. And this is the standard A-star algorithm developed in the late 1960s by Niels Nielsen, actually for performing path planning for a mobile robot. And this is the general informed graph search algorithm. So let's see how we can use it or will use it in robotics for performing navigation in practice. So now we're looking to the application of this A-star algorithm to, let's call it, simple robot navigation. We start with a simple robot navigation in the sense that it's a 2D map of the environment, a grid map that we have, and we assume if a robot sits here, it can travel to all its neighboring states. So you can achieve this by rotating the robot on the spot and then moving into one of those cells. So this is, for example, a neighborhood relationship, the 8 neighborhood that we can take into account for planning. If I don't allow the system to walk diagonally, then I could use the 4 neighborhood where only those 4 neighboring locations are possible. And then if we have a grid map, so again here dark is an obstacle region, the system is right now over here and we want to reach this state over here, then I can expand the nodes and you can see it here, this kind of grayish area. The darker the gray values, the larger the cost of the nodes. Actually, this is the expanded region. I'm expanding the nodes until I actually find my target location. And that's how we typically, well, that's what we want to achieve. What we would like to avoid is that the robot collides with an obstacle, and consider the assumption here is that actually the robot actually fits into one of those grid cells. This may be the case if you have a very coarse discretization of your environment, but in reality your discretization of your map is typically finer than the size of the robot. Let's say you have a 10 centimeter grid discretization, but your robot is typically larger than 10 by 10 centimeters. So then you would need to expand those obstacles in your map as in order to avoid that the robot will actually bump to obstacles. So you need to disallow the robot to actually move too close to a wall. And there are other tricks that you may need to take into account to avoid that the robot doesn't bump into obstacles, because the size of the robot is bigger than your discretization of the space. So what are typical assumptions if you use A-star based path planning for mobile robots? The first thing is we assume we know where the system is. So we assume our localization system works. Because if our localization system doesn't work or makes large mistakes, then we may not be in the state where the system thinks it is in. And then, of course, the planning system is likely to make wrong assumptions on the way and may lead to collisions or at least to suboptimal path. So the planning algorithms itself, most of them assume the robot location is known. So we know where the system is. And then the system computes its path based on a map of the environment, for example, an occupancy grid map, assuming that the map is actually correct. Right? So it doesn't assume that the map may be wrong. And it assumes the world is how the map tells me it is. And then it computes its paths and then executes those paths. And so the question is, are all those assumptions actually always true? Do we always know where we are? Do we always know that our map is a good representation of the world? And can we always just execute the motion commands that the system will give us? And obviously, this is not the case. Those assumptions are assumptions and they can be violated. So there are different things that can happen. For example, the robot may be slightly delocalized. So the robot may be at a location which is not the actual location where it thinks it is. Maybe it's 10 centimeters off. 10 centimeters off may not be a problem in large spaces, but if you need to navigate through a doorway, 10 centimeters off can be actually problematic. And so the robot can be slightly localized and this can be problematic. The other thing which is problematic is that the planning algorithms typically compute the shortest path, right? So that's something that we put in by design. Find me the shortest trajectory to the goal. The shortest trajectory to the goal, however, will go very, very close to obstacles because you're basically trying to find the shortest route. So the robot will pass as close as possible to obstacles, for example, if it drives around a corner. And that's a behavior that I don't necessarily want to have, even though I prefer short trajectories. Other problems could be that the alignment of the planned path or planned trajectory is not in line with the structure of the grid map. So if you have, for example, two nodes which are a little bit away from each other, let's say one is a little bit higher than the other, the straight line distance may be the shortest path in here, but if you plan the path only with a 8 connected grid, for example, the robot may make only 45-degree turns. So we will get a trajectory which is actually not the optimal trajectory and may look a little bit weird. Although it is in the abstraction of our world to this grid map with an 8 neighborhood, the optimal path, there's not the optimal path in the real world. And that's something that can happen to us. One of the things to deal with the fact that the robot may be slightly delocalized and that you would like to avoid the robot to go very close to obstacles, so the kind of the first two things, is you can do a trick in here. And this is kind of an approximation or a trick avoiding the robot drives very close to obstacles, and it kind of keeps a security distance. The problem is if you just expand your obstacle, you just make your obstacle larger in the map or virtually for the robot, that it keeps a longer distance, this will actually lead to the problem that very narrow passages cannot be traversed. So there may be situations where the robot really needs to fit just through your obstacles and you still want to be able to navigate through those spaces. But in general, you would like to take the robot a larger safety distance to obstacles. So how can we actually do this? And one thing we can do is we can actually convolve our map with a smoothing kernel. So we can smooth out our occupancy grid map. So what does smoothing do? So what the Gaussian kernel or a Gaussian blur basically does, it blurs an image. It smears information kind of between neighboring cells. So you may have seen this if you have a photo, a perfectly sharp photo, and you apply a Gaussian blur filter to it, you will see that everything gets blurry. And it happens basically by distributing color information from one pixel to its neighboring pixels. And we're doing something very similar here in this grid map. You can see the grid map as a black-white image, right? So either as an obstacle or there's no obstacle. What we can do is we can take some of the, let's say, black color and smear it into the neighboring white cells. So this will lead to a white cell, which turns out to be, let's say, gray, because we mix white and black in there. And gray means, I can go there, but probably I shouldn't go there, at least if I can avoid it. You can see this kind of as a very coarse approximation of what the robot thinks. So it says, I prefer actually white cells, black cells are forbidden for me, and the gray cells, I should stay away as long as I can. And this basically, this convolution of the map provides you with increasing the distance to obstacles, but still driving on a short path. So for example, let's say we have a 1D example over here, and we have two cells which are occupied, so probability of 1, and the others are free space. So what the convolution will lead to, it will lead to a distribution, if I in this case, convolved it twice with a binomial kernel, then some of the white information will smear into the originally black information, and the other way around, some of the black color or occupancy probability will smear into the free space. So if you see now the probability, let's say as cost, or you can turn probability into cost, the higher the probability, the higher the cost, then you would see the robot would actually try to stay away from the obstacle, maybe drive here in this direction around grid cell 4, but if it can't do better, it would drive on 3. If this still doesn't give you a solution, it will drive on 2, and so on and so forth. So it would try to keep the distance to obstacles. What you would probably do is you would actually take both of those maps and then take the maximum out of those costs. So you still want to have the occupied space to be really forbidden because we know there's an obstacle, but the other cells would still cells the system should avoid. So how can this convolution be computed? This is a standard convolution, and here with a kernel of a fourth, a half, and a fourth, which is a binomial kernel. So if you want to update a cell x or xi y, then you take half of the value of the grid cell. So this is the same value, the new one, the old one, half of it, plus a quarter of the neighbor to the left plus a quarter of the neighbor to the right. And you can do this in x direction and y direction, and kind of gives you a Gaussian blur. It takes a binomial kernel to blur that map, and you're basically smearing probability mass for occupancy into the white space. And if you then plan in this convolved map, you will lead to trajectories which are slightly longer, but make slight detours next to obstacles. Unless you have a very narrow passage where the system can't pass by otherwise, then the system will actually drive through this narrow passage. So what we're doing most of the time is we are performing the A star in this convolved grid map. And this will produce paths which are slightly longer because we are kind of making a small detour around occupied or probably occupied cells. But it keeps the robot away from obstacle, and this is kind of a fast and quite reliable technique if you have moderate noise. And moderate noise can be moderate noise in your localization, let's say you're a few centimeters off, or moderate noise in your motion execution, because the system will often not always exactly execute what you tell the system to do. If you say, go a meter forward, maybe the system goes a meter and 1 centimeter forward. And if you plan very precisely without taking convolutions into account, this 1 centimeter more may already lead to a collision. So this convolved map is something that you also need to take into account if your system does not precisely execute your command. You can actually see this as some form of simple approximation of a Markov decision process, something that we will discuss in the next lecture. But this convolving a map before planning it is a standard approach that most planning systems do today in order to keep the robot away from obstacle or keep some distance to obstacles. A further thing about the heuristic I would like to mention, because it's also something that is very useful, is computing a heuristic via Dijkstra's algorithm. So why should that make sense? See it the following way. In practice, we don't execute the A star planning just once to reach a goal location and then blindly follow that path. We are executing this A star planner over and over again. Why do we do that? Because the robot moves through the environment, it may deviate slightly from the previously computed path, so we cannot just follow that path, we need to plan a new path from the location where it is. Or alternatively, the world may not be static. People may be moving around. New objects may be placed in the world. And we're using our sensor data in order to update our map. That means the map may change, and as a result of that, we need to plan again a new path. Most of the time, however, the path will not change or will stay more or less the same. So what we can do, if we know that we need to plan multiple times, we can put a bit more effort into computing a heuristic with a kind of more expensive algorithm, so that all the subsequent planning steps are as fast as possible. And this is something which we can do with Dijkstra's algorithm. So if you run Dijkstra's algorithm starting from the goal location and expanding it through all cells, what you have is the exact cost from any cell to the goal location. And this is the optimal heuristic, the best thing you can do. If the world wouldn't change, you just need to make a gradient descent in this in the result of the Dijkstra algorithm. But given that we may see unforeseen obstacles, so new things popping up in our world, this may not be the case. So I still want to run the A star algorithm, but I want to reduce the computational cost of the A star algorithm as much as I can. And I can do this by running Dijkstra's algorithm and use this cost as the estimate for the heuristic. So even if a new obstacle pops up, it will only increase the cost, then the heuristic will not be optimal anymore, but it will be very close to the optimal solution, and clearly better than the straight line distance. So then just running, relying on this Dijkstra result on the map computed once and using this as a heuristic for my A star will dramatically speed up my search. So here's a small example. So for example, this is my goal location over here. White means low cost and dark means brighter cost. You can see here the kind of cost field that is computed from Dijkstra's algorithm. And so the darker the cost, the higher the estimated cost to the goal. And so we basically need to follow that gradient in order to reach our target location. And we can use this directly in order to guide also our search in A star by always choosing the path which has the highest expected cost to the goal. So whenever you need to plan more than once and speed matters, then consider to use Dijkstra's algorithm to pre-compute a heuristic, which is then the optimal heuristic in case the world doesn't change. But if you add new obstacles to the world, you still have an admissible and very good heuristic so that A star is executed really, really quickly afterwards. So this is basically the standard planning problem in 2D when we have a robot that moves within the 2D world. A simple robot moving on the plane. We will get out a trajectory. This trajectory will typically pass to a local collision avoidance system and a path following system that then follows this path and guides the robot to the target location. We can, however, also go a step further and try to integrate this path execution or collision avoidance by planning in higher dimensional spaces, as long as we can execute the planner fast enough. So how do those higher dimensional spaces look like? Again, so far we just considered the XY space, but in reality the orientation of the platform matters and also the velocities of the platform matter. So what we can do is we can go into a 5-dimensional space, taking into account, beside the X and Y location, also my yaw angle, so my angle theta, as well as the translation velocity and the rotational velocity into account. And now plan with the robot also taking into account kinematic constraints, for example, that we can't accelerate from 0 to maximum velocity within one time step, or that we need to decelerate even if we can make an emergency brake, but maybe we don't want to make an emergency brake, we want to brake down more gently, to provide smooth trajectories. And all this can be taken into account if I extend my planning problem from a 2D planning problem into a 5-dimensional planning problem. So where I expand the state space from 2 dimensions into 5 dimensions. So that then a sequence of those states will automatically give me a sequence of motion commands that the system should execute in order to reach the location. So from that path that I have, I can directly read out the translation velocity and rotation velocity when and execute that directly or send it directly to my low-level controller. So how does my search space actually looks like? So my search space is this 5-dimensional space. So that means from state x1, x2, theta 1, v1, omega 1, I can go to x2, y2, theta 2, v2, omega 2 by executing a motion command, v2, omega 2. And I may need to take into account an acceleration constraint, so that the difference between v1 and v2 must be smaller than the maximum acceleration, and the same for the rotation velocity. That means I have bounds with how fast I can increase my velocity or decrease my velocity. So that as a result of this, the next configuration of the robot is x2, y2, theta 2, of course with the velocity commands, and the velocity commands then directly provide me the motion command that I need to execute in order to follow a trajectory like this. Again, only up to the discretization of the state space that should be taken into account. Okay, in theory this sounds great, but the problem is, in reality, that going from a 2-dimensional space to a 5-dimensional space is computationally quite demanding, because the number of states that I need to represent grows exponentially with the number of dimensions of my state space, of my search space. And so I typically cannot execute this fast enough. Let's say for an indoor robot, I typically need to have at least 5 Hertz in order to check for obstacles. If I'm going, let's say, with a speed of up to 1 meter per second, maybe 5 Hertz is sufficient. But if I would even go to higher velocities, I would need to increase this frequency. And that's something which is hard to achieve if you really plan in this 5-dimensional state space. So what we need to do is we need to do better than planning in that 5-dimensional state space. And the solution, or the key idea, is that we can gradually build this up. So we start from a 2-dimensional space and then extend the state space so that not the full 5-dimensional state space need to be taken into account, but only a small subset, that is likely to contain my optimal solution. We can do this by an approach basically taking 4 main steps into account. The first thing what we do is we take our occupancy grid map or 2D map and use the current sensor data and update the map. So if we have an obstacle moving through the environment, either an unforeseen obstacle or maybe even a person walking around, we will add this information to our map. So the map then becomes just a very short snapshot, or a map that is only valid for a very short amount of time. Let's say for a fifth of a second, or for a third of a second, or a tenth of a second. Is this the current representation of the world given our sensor data and the map information that we had before? Okay, then we have that updated grid map, and what we then do, we plan in 2D a path with a star that finds a 2D trajectory from our current location to the goal location. Basically what we have done before. And we execute this and get this 2D path. And the problem is this path only exists in 2D. It only has x and y information, and doesn't have further information like velocity information or heading information into account. But the assumption in here is that the 2D, the path we plan in the 5-dimensional space should actually be not too far away from the 2-dimensional path, because we know already that the 2-dimensional path is actually the shortest path, but not necessarily the fastest path. But fast and short is typically not too far away from each other. It's not the same, but it's often not too far away from each other. And we can exploit this by saying, okay, let's build up this 5-dimensional space only in the close vicinity of this 2-dimensional space. So that we basically build up a restricted 5-dimensional space where we say these x, y locations should be really close to the path that we have computed in step number 2. And this will dramatically reduce the search space in this 5-dimensional space, that we basically just look within a small channel or funnel around this 2D path that has been executed. We'll now go through these 4 steps and see how that actually changes our setup over here. The first thing we need to do is we need to update our grid map. So again, the environment is assumed to be represented by a 2-dimensional occupancy grid map, as we have discussed it here in the course beforehand. And we may have performed the convolution to increase the distance to the obstacles. And then if we see new obstacles, with our sensor data, we update our map just by adding this additional information. So we basically take our original map and overlay it with the additional information that we have from our sensor data. So if the robot is currently here, this blue dot over here, and we see obstacles in the environment, we will add those obstacles to the map. These are kind of these 3 blobs over here, which are obstacles based on the current sensor information. And it's important to note is this map stays constant. This is our static map, and this map is just kind of a combination of what we see right now integrated into that map. But we basically always start with this map and just take our current sensor data into account to kind of augment the map. We won't remove anything from this map. This map will always be valid. We just add additional information out of this. And when we don't see the obstacle anymore, those objects can be removed again or will be removed again, but nothing from the static world will actually be removed. Then the next thing we do is in step 2 is we use the standard 2D A star algorithm to plan a path from the current location to the target location. So consider that this is my goal location, this is the current location of the robot. Then I use A star with this heuristic that I computed via the value iteration or Dijkstra's algorithm. It's both equivalent in this case. The deterministic value iteration is Dijkstra's algorithm. Then we'll get a path which looks like this, which drives the robot around, keeps obstacles, and reaches this goal location. Okay, so this is the 2D path that I have computed. So what I then want to do is I want to build a small region around this 2D path, and only in this area expand it to the 5-dimensional space. So the projection of this 5-dimensional path onto the XY space should be close to the optimal 2D path. This is basically the underlying assumption. So that means that the shortest path and the fastest path is not too far away from each other. This is the case most of the time, but of course it is an assumption that we're doing here. And depending how large or small I define this area, I may increase the computational cost. So what we construct is we build kind of a channel or this kind of 5-dimensional funnel around this 2D path, around these XY locations. We basically restrict the space in X and Y and then perform the high-dimensional planning only in this restricted search space. And this can be illustrated over here. So we may even not have enough computational resources to fully plan towards the final goal. So we select a sub-goal, let's say, 5 meters ahead on our path, and then build this blue region here which is, let's say, a region, whatever, a meter to the left and to the right-hand side around the path, and we say, okay, only in this region we are building up our 5-dimensional space. That means in all the other areas we don't even build up this 5-dimensional search space. We stick with our 2-dimensional map and the path computed to it. And only within this blue region, trying to reach this sub-goal, we are building this 5-dimensional path. And then we use, in this 5-dimensional space, the A star and compute the 5D sequence of states, so that we then can directly take out the steering commands, translation velocity and rotation velocity, to reach the sub-goal. And then we repeat this process over and over again, and also shift the sub-goal further towards the goal. And this is something that I can do quite quickly by taking as the heuristic into account the cost that I have from my 2D value iteration or 2D Dijkstra's algorithm, because this is still a lower bound for the actual cost that I have. Because if I need, for example, to rotate on the spot, I can take the maximum rotation velocity and add it to the node. So I can fix this, improve this a little bit, but in general, the 2D heuristic already provides me with a good idea on how the cost could actually look like. So also having a small example over here. Again, what you're seeing is this is this channel, and then the 2D path, maybe this path over here, and the white path here is the 5-dimensional path, which you can see generates a smoother trajectory because it takes a different translation and rotation velocity of the platform into account, and it's not forced to this 8 neighborhood, because the transitions are computed based on translation velocity and rotation velocities. And then I can actually start this small video over here where you see how the system moves through the environment and how the channel is moved forward all the time, and you can see how the system follows those white dots, which especially within the curves deviates from this 2-dimensional path. And you can see here in effect, given that the sub-goal doesn't know where the final state is, the system made a somewhat bigger curve here, and this led to a slightly longer trajectory, but typically a trajectory which is close to the optimal solution, and we get a very smooth trajectory that the system can follow. And if we can execute this, which is the case here, multiple times per second, we can actually run that on a real robot and estimate or update our path based on the information that we see. Also a small example, in the real world, the system navigating through the environment, Robot Albert at University from Freiburg, and you see here the planner that updates the map. You see this channel, that's me over 20 years ago doing this experiment over here, how the system navigates through the environment and smoothly drives around obstacles, and then is also able to drive through rather narrow passages or a doorway in order to reach the final target location. So by using this channel around the 2D path and planning the velocities and orientations and XY locations within this small area, we can actually generate smooth trajectories for the robot platform. A few words maybe, how does this relate in terms of cost with respect to an optimal solution? So optimal solution means here I'm computing the 5-dimensional space over the whole grid, over the whole environment. And we can see if we make this channel very small, like here 1.50 meter long and 35 centimeters to the right and left-hand side, we will have an overhead of something like 10% in terms of runtime compared to an optimal solution. But as long as we make it larger, like with a width of a bit more than a meter and 5 meters in front, then the costs are typically small or neglectable with respect to the optimal solution, and we reach something which on average is more or less the optimal solution, although this is of course not a guarantee. This is just based on a series of experiments. You're not guaranteed to get the optimum, but in practice you're close to the optimal solution. So this is one example how you can use A star not only for planning an XY path, but also planning in more complex, in this case 5-dimensional state spaces, which you can use in order to combine planning and collision avoidance. Always assuming that you can execute this fast enough, but that is not a problem on today's hardware anymore. It was already possible around 20 years ago. So to sum up, robot navigation often requires planning because systems need to know where they should go. Robots often should reach a target location or maybe even cover a space where you also need some form of planning, although a slightly different planning technique than what I've shown over here. And kind of the gold standard for performing this planning today is the A star algorithm. at least if you can discretize your state space, because you're doing this in a two-dimensional world, for example, A star is kind of the first thing you would try in order to do that. What A star does, is a combination of a greedy search together with a heuristic in order to estimate how expensive is it to reach the goal location from a given target location. And through this combination of real cost plus estimated cost to the goal, the system is able to find solutions very quickly and plan paths very quickly. And we can also extend this if we, this was kind of the last part of this lecture here, if we go to more higher dimensional state spaces, taking additional things into account like velocities, we can incorporate kinematic constraints like braking and acceleration behaviors, and we actually generate better trajectories that are not aligned to this 45-degree grid structure, where I can only go in 45-degree orientations, but actually generate smooth trajectories for mobile systems, also navigating elegantly through confined spaces, which is very convenient. The resulting path that we get with these planning algorithms are typically optimal solutions or close to optimal solutions. The question is, however, how well does the abstraction towards this simplified planning problem or simplified representation where I execute my path actually reflect the real world. So if I make a lot of assumptions turning the world into a 2D grid map, even if I have an optimal path in the 2D grid map, it doesn't necessarily is the optimal path in the real world. But often the paths that I get are not too far away from the optimal path, and what most planning systems today do, they will plan a path on this lower dimensional representation like a 2D grid map and then perform some subsequent optimizations, for example, making trajectories smoother or taking kinematic constraints into account. We can do this directly in the planning step as I have explained it here, but there are also other ways for doing this, as for example, fitting splines into those trajectories and optimizing those splines so that they're still collision free, but are optimized, for example, to maximize the velocities or get certain speed profiles taken into account in order to generate trajectories which the system can follow smooth, but still are guaranteed to be collision free. Okay, that's it from my side. That was a short introduction on how to do path planning with mobile robots. I'm just taking into account low dimensional spaces here. So we haven't talked about how to plan the trajectory of a manipulator, for example. This was just kind of simple navigation in the 2D world, and for that the A-star does a really good job and will solve most of your problems. Again, if you go to high dimensional spaces or have very complex, more complex constraints on your system, or cars driving through the environment at much higher speeds on roads with different road participants, you may take a different approach, but for simple indoor navigation, that is kind of the first step to do here. So thank you very much for your attention, and I hope you get an idea how those planning system works by now. Thank you.